So today what we're looking at is other sorting algorithms. Uh, we so far saw sorting algorithms of the n squared variety. Namely the selection, bubble, and insertion sort algorithms. Today we're going to look at two algorithms which are much better than these order n squared algorithms. These are the quicksort and merge sort algorithms, which perform much faster than and the time complexity is in the the best case for both these algorithms is theta log n. In fact, merge sort guarantees a worst case complexity of theta n log n. Quicksort, on the other hand, in the worst case can be theta n squared, and but in the best case it can be as good as log n, and we will see why. Okay, but why is quicksort still called quicksort? Is still called quicksort, and this was actually designed by Hoare, one of the founding computer scientists. In fact, Hoare rules is what we used for proving correctness of programs. Okay. And he is also responsible for this. So let's see how quicksort works. Let's take an example. And what we do is the following. Today morning's lecture, I had actually made a mistake. So this is a replacement recording for what I have done in the morning. And let's take this example. Let's say these are the elements that we have. This is the example that we took. Made some mistake in the morning. So what we do is both quicksort and merge sort actually recursively divide an array into two parts. And therefore, they use the paradigm of what's called divide and conquer. We saw this earlier in the context of binary search, but there it was only one part which was which the focus was on. Here, on the other hand, we're going to divide the sorting problem into two parts and work on each part separately. In merge sort, it exactly divides it into two. In quicksort, it will depend upon what is called the partitioning element. Okay. So let's look at this example, how it works. So what we do is we define this partitioning element initially to be the middle element. Okay, let me call it X. And let's say this is left and this is right end of the array. The reason why I'm not putting 1 to n or 0 to n minus 1 or whatever is primarily because since it's a recursive algorithm, and we're also going to use a recursive algorithm, in the recursion, it will process one part of the array whose bounds will be defined by left and right. So let's see how this algorithm proceeds. We start with these pointers left and right, and we also use, and let's say this is an array of left dot dot right of integer for the time being. It can be any kind of elements as long as you can define an order. That is, you can say between, if I given a pair of elements, you can say which is larger, which is smaller, and so on. So given this, what it does is the following. Let's see, this is what we have. So this is the pointer to left, pointer to right, as I already mentioned. And I have two other pointers, I and G. And the objective is of quicksort is the following. What it does is it chooses what is called a middle element, and it compares the element at I with respect to the middle element at J with respect to the middle element, and checks whether they are in order or not. So if you look at this, this is 17. So 17 is smaller than 42 because we are sorting the array in ascending order. 44 is larger than 42. Therefore, these two are 44 and 17 are out of order with respect to 42. So what we do is we simply exchange these. And then what do we get here? We get 17 here, you get 44 here, 55, 12, 42, 94, 18, and 6 remains as it is. Now, clearly, this is in order with respect to array 17. So we move to the next step. And similarly, 44 is in the correct side with respect to 42. So you move to the next step. So this is I, this is J. Again, you find that these two elements are out of order. So what do? We move it again. We exchange them again. So you get 17 here, you get 6 here, 12 here, 42, 94, 18, 55, 40. Okay. Now what happens? You compare this, 12 is correct with respect to 42, and then it comes to 42 here, which is not less than. And similarly, when you come to J over here, J is not in the right order with respect to 42. So you keep the pointer here. This is I and this is J. I'll tell you why it stops over here. So we're looking at a situation where while, let me call this array V or array, while A of I less than X, do I plus plus, while X less than A of J, do J minus minus. Okay, this is what we do. Okay, so clearly what happens, A of I is not less than X. Okay, it's equal to, so we stop here. Now, what is interesting about quicksort is the partitioning element itself can move. So what will happen now? We have 17, we have 6, we have 12, and 42 and 18 will get exchanged, 94, 42, 55, and 40. Then what will happen? You will have I gets incremented because 18 is on the right side. Similarly, 42 is smaller than X less than A of J. So where are we now? We've already exchanged this. So we move this pointer away. Because both of them are exchanged, the pointer has been moved. X is not less than A of J, so it moves. So it's the same place. Then what happens is it goes through one more iteration. This is I and J. So what happens is now, since 94 is on the wrong side of with respect to 42, what will happen is we'll have that J moves over here. This was a mistake that I made in the morning. So it remember 6 and 17. So J will move here and I will remain here because it is at the correct place. Okay, then what do we have here? 42, 55 and 44. Why does J move here? Because 94 is larger than 42. But in the meanwhile, what has happened? The pointers J and I have crossed. Okay, since both have crossed, what will it do? It will stop that pass through the array. And now you start processing the array from left to J over here and from I to right over here. Okay, that will be the next pass of the sort. So now let's see what happens with left here. So what do I have here? 17, 6, 12, and 18. So again, you start with I and J in this part of the array. Then this is your middle element over here. Then you have 6, which will move here because 17 is smaller than, these are all larger than the middle element. So what will happen? J will come here and 6 and 17 will get moved. Exchange, and this what will happen. So what will happen now? Now your array size becomes 1 here. This is left and this is also J and this is I and this is right. Okay. Then the same processing will happen. This is the middle element. And again 17 will move. We have 12 here. 17 and 18. Now 17 and 18 will be one element over here. And again, this will, again, the 2 pointers will cross and this is in order. And this is your pick sorted portion of the array. And then what will it do? It will start with 94 again. 94, 42, 55, 44. And this is left, this is right. Again, this is I, this is J. And again, this is the middle element. Compare this is on the wrong side. So 94 and 42 will get exchanged because all the others are in the correct place. 42, 94, 55, 44. And then you have one element over here and 3 elements here. And the story repeats itself. And you will finally find this portion also sorted. Notice that here it's becoming 1 unit and 3 elements long. And you will get here 42, 44, 55, and 94. And then you have the complete array sorted. Okay. I'm sorry, I made a mistake this morning and I'm just correcting this. So let's write this algorithm for quicksort. And let me see. So, okay, let me write the algorithm for quicksort. P module, quicksort. I've used array V in my argument, so I'm going to leave it as it is. V is an array of n integers, let us say. Then I also have a pointer left, comma right, which points to the particular nibble of the array. Okay. Now I start with int I, comma j. I need 2 variables like this. I assign I to left, assign j to right. It starts with the 2 centering points. Then I assign x to the b of left plus right divided by 2, the mid element in the middle. Then I use a repeat until while block. The various ways in which one can write the quicksort program, but I prefer this. While b of I less than x, do I to I plus 1, while x less than b of j, do j to j minus 1. Okay. Then look at this here. If I is less than or equal to j, this is the important point, then swap b of I comma b of j, increment I, and so the pointer from the left is implemented from left, and decrement the pointer from the right. And I do this until I less than or equal to j. Then if left is less than j, then quicksort of v comma left comma j. If I is less than right, then that means it's not a single element array, that particular nibble of the array, quicksort v comma I comma right. Okay, I'll explain this algorithm in a little while. So this is where, so what happens is when we saw that example where we saw 94, we saw the pointer to 94 in quicksort. For example, this pointer is here. Then how is it fixed in the algorithm? It's fixed as follows. What is done is here, so when you have I and j, for example, until I less than or equal to j. So it'll go back here, then it will increment I. And I'm sorry, the I will remain correct because the next element is 94, which is greater than 42, so it's in the correct side. Then it will stop there and it will stop at 94, but it will decrement j. Then what will happen? I is at 94 and j is moved one pointer before. J becomes I minus 1. When j becomes I minus 1, the two pointers have crossed and it will stop. Okay, this is what the algorithm will stop. Okay, and it says here if I less than j, less than or equal to j. Otherwise, it won't get done. And then it goes on does the quicksort on the respective portion of the array. Analysis of quicksort, we will take it up a little later when I do merge sort. Okay. And quicksort and merge sort will be done together. Okay. So let me stop here. So this is the replacement video for today's lecture. I will upload the video today.